everybody, this is Rashi Berry from Columbia University, your host for Daily Physics. Today, episode 10, our topic is space-time. Can you draw x-axis and y-axis?
What's an x-axis?
X-axis is meter.
I'm just kidding, I know.
Y is also measured in meter. All right. Can you put a cat at 0, 0 or something, an object at 0, 0?
Okay.
Okay. All right. So can you put that object at 0, 5? Different object. Say cat number 2, 0, 5. Oh, 5, 0. I'm sorry. 5, 0. Okay. So, all right. Isaac, what is the distance between these two cats?
5? And also, I didn't draw cats, but...
Okay, it doesn't matter. Okay, Raf, now can you put another diagram? Oh, Isaac, can you put diagram number 2? Raf, you can do 2. Diagram.
What are the x and y axes?
Same thing. Okay, now can you put the cat at 1, 1? Put the cat at 1, 1.
Cat 1 or cat 2?
Cat 1. And cat 2, 5, 4.
5,
4. 5, 4.
Okay. Isaac, you are blocking.
Yeah, I'm trying. Sorry.
So what is the distance between the two cats? Isaac.
It's 5. It's 5.
Okay. So what can we say? Distance is distance absolute?
All we know is that there's one situation in which their distance is 5 meters, and another situation in which their distance is also 5 meters.
Raf, why are you nodding your head?
Oh, well, yeah, the distance stays the same. Even
Well, yeah, the good thing about reference frames is that with Galilean transformations, distance is preserved.
So how this show that the distance is absolute?
Well, you have to first...
Okay, even, let's say we draw a line between the two cats here and here. So this line has no y component. It only has the x component. But this line has the x and y component.
Orientation is not preserved.
But they both have
x is 4 and y is x is 4 and y is
3.
3. Okay.
So, but even though it has different components, the total length is the same. So
well, yeah, orientation is preserved through Galilean. No, orientation is not preserved through Galilean transformation.
So the same idea, yeah, there's the same idea holds in relativity, except instead of distance, you replace it with space-time distance.
We do one more example. Can we do Earth and Moon? One observer on the Earth, one observer in the middle of Earth and Moon, and one observer in the spaceship.
Wait, one observer on the Earth, one
observer on Earth, and sees that the Moon is moving around the Earth.
Okay.
Moon is moving around the Earth like a circle. Can you draw that? Okay, like a circle. The other observer is in the middle of Earth and Moon. He sees that the Moon is moving like this. This is Earth. The Moon is moving like this. Another observer. That's another observer.
Okay. So, okay, let me think. Then let me put this observer maybe somewhere here. And they see the Moon is moving like this.
Yes. Yeah. Okay. More or less like a straight line.
Okay.
Or like when you throw a ball with 90-degree angle.
So observer 1, observer 2 is outside or inside the Moon's orbit?
Is in the middle, somewhere in the middle of Earth and Moon system.
So they see the top-down view. They see
top-down view. Yes.
Okay. So it's like right here.
Yeah, could be. Yes. It could be. Raf, draw it. So he gonna see it like this when you throw it.
Yeah, I'm a little confused because your second observer is like outside the Moon's orbit.
No, they see the orbit as like a line because they're edge on to the orbit. So the orbit just looks like a line if you look at from the
I see what you mean.
Yeah, skill issue.
Yeah, but that is still, that effect is preserved if he stands like right here. So all he'll see is like a sinusoidal oscillation back
Yeah.
and forth in line.
Okay.
All right. So they would view it differently. So the geometry would be different, but the space would be absolute for them, right? The distance between Earth and Moon system would be same, 3.84 times 10 raised to 8 meter. Is that right?
Yes.
Yeah. Yeah.
Okay.
Yeah.
Distance is always preserved.
Is it for Newtonian
In
mechanics?
Galilean
Or is it for Newtonian mechanics or is it for special relativity?
Newtonian mechanics. Of course, in special relativity, distance by itself is not preserved.
Okay. All right. Great. So Newtonian mechanics.
The space-time invariant is the only invariant thing.
Okay. So Newtonian mechanics distance is absolute, right?
Yeah.
Yeah, in Newtonian mechanics, it's the invariant. In Newtonian mechanics, distance and time are the two invariant things.
Okay. What about time? Time is also absolute, Newtonian mechanics.
Yeah, time is invariant
Yeah.
between reference frames.
Okay.
Those are the only two invariant things in Newtonian mechanics, but it happens that in relativity, the only one thing that's invariant is a combination of those two.
Okay. So let's do that.
Can I show you an example?
You're gonna show the example. Let first check what mistake Rap makes.
I don't think Ref's gonna make a mistake on something he studied for like 4 years.
Rap, what is C?
Okay.
C.
Okay.
So what do you want me to draw then?
You can draw.
Oh yeah, that's useful because now any
You can draw a
distance
wall
between
line.
two points-
Help us understand the wall line.
Okay. So if someone is just standing still.
Cat. Use that cat example.
Wait.
Okay. So imagine you have a cat that's just standing still. Then
No,
they're not moving.
cat at 0 second, cat at 1 second, cat at 2 second.
Yeah. So
its
I'm
line
gonna-
is just going to be directly vertical.
Okay.
Because
So
it's
cat
not
at 1
so
second, cat at
Wow.
1 second, put 3 meter.
Why are you saying wow, bro?
Okay, cat at 1 second, cat at okay. So what is this? What do we call
Yes,
this?
I know what a space-time diagram is.
Okay, so this is, for example, the cat at 1 second, at 2 seconds, 3 seconds. Yeah.
Okay.
So this means even if the cat is standing still in space, it will be moving in time.
Yeah, absolutely, absolutely. I don't have any control over time, but I have control over space. I decide not to move from here, but I cannot decide
To
move
stop
from-
moving through time.
Yeah, and of course, if something is moving over
Now,
time.
if something, okay, yeah.
Okay, 1
We're
second.
gonna look
Let's see
something
what
like
Isaac
this.
is doing. Okay, now this guy is moving. This guy is not standing still. So this is also wall line. Can you write the wall line? So
The
can you
world
write
line? Oh,
walled line? Ref, can you also write the walled line? Now,
yeah, it's the path through space-time that something is currently taking.
your goal is to help us understand that 45 degree from 45 degree from origin and 45 degree, so that you can show that future event, past event, and the independent event, and that both 45 degree diagonal line, meet at a point, let's call 1. And with respect to that 1, you're going to show us future event, past event, and independent event.
Yeah, hold up. So, can I talk for a second?
Yes.
So, normally, when you see steeper lines, you think about faster ascent. But because of the way the axes are shaped, if you have something that's moving slower, like this object, then its world line is actually going to be steeper than something that covers more distance per unit time.
Yeah.
So the steeper something is, the slower it is. And now, when you think about it, what's the absolute limit? Well, there's a reason why we have this proportion C right over here. If we have 1 meter here, then the equivalent here is C seconds. So now, what would a beam of light, what world line would a beam of light take if it started at 0 meters at 0 seconds?
If C is one space, C is one space over time, then it's 45 degree.
Yeah. So, in 1 second, it's going to travel C meters. In 2 seconds, it's going to travel 2 C meters. In 3 seconds, it's going to travel 3 C meters. And because of this proportionality constant right here that we add onto the time axis, instead of looking something like this, the world line of a light beam is exactly a 45-degree angle. Don't take that hand out of context. Which means that anything that's not light will have a world line that falls within this area, or, over here.
Okay, great. Now, as Isaac did like this, can you also do like this and call it future, call it fast, and call this one event 1 and call this one, help us understand why this two is independent event, but these are dependent.
Yeah.
You want to
Yeah,
explain that?
I can do that.
Oh, did you see me doing that?
How to do what?
Did you see my blackboard?
Yeah.
Oh, okay.
So yeah, Isaac explained it pretty well, surprisingly well. So let me draw the space-time diagram again. And let's say we have some event.
C is missing.
Okay.
Holy
yeah.
hell!
So let's say we have some event. This could be a fireworks, or it could be some party, any event. So at this event, we can draw the
Yeah, light.
lines
Okay.
that show the speed
Yeah,
of light.
explain the wall line, two wall line.
So
Yeah.
these two world lines are at 45 degrees, and they represent the speed of light. So only light can travel at this speed. Anything slower than light is going to fall into these two cones.
Yeah. Okay.
So this over here is the past cone. This is the past cone, and this is the future cone of the event.
Mhm.
And this is the present cone. This is the present moment.
Yeah.
And anything outside is sad, because anything outside of the light cone cannot affect it. It has no causal connection with this event at E. And why doesn't it have any causal connection with the event E?
Wait, can
Because
I explain it?
these travel faster than the speed of light, which
Yeah,
is
baby.
impossible.
Go ahead, explain.
Yeah.
Okay, you go.
Okay. So think about that party as sending off light in every single direction. Like all of the neighbors were seeing the party, etc. Now, since this is a 1D party, sending light in every direction means sending a firework this way and sending a firework that way. Now, light going in the forward direction is going to take this world line. Light going in the backward direction is going to take this world line. And of course, as I explained before, because of this proportionality constant, both of these world lines are going to take a 45-degree angle. And as Ref said, anything outside here is going to be sad. Why? Because the light cannot ever reach them in time for them to actually affect this event. So as you can see, the light is just missing them. For this to have any effect, light would have to go this fast. But it can't. Nothing can exceed light speed of 45 degrees. Nothing can be this steep. Well, or this non-steep. And so, that means that this event cannot have any causal connection to this event because it's totally outside the reach of light that's being emitted from this event. But of course, something that's within the light cone can absolutely have, or in this case, this can absolutely have an effect on this event. But this cannot have an effect on the event outside its light cone.
What would be
so that's essentially what Ref is saying.
What would be the example of this? For example, if I turn on the light, a moment later, the light bulb turn on. Is that cause and effect? Would that be a cause and effect?
Well, yes.
So
you flip the switch. So you flip the switch, which is a cause, and the effect is current flows through the light bulb's filament and turns it on.
Well, nothing can happen instantly because information travels at the speed of light. So
actually, I think that the difference between turning on a light or turning the switch and the light actually flipping on is a lot slower than the time it takes light to actually reach the bulb. That's pretty much instant. I think it has more to do with the strength of the wiring, for example, which affects the speed of the current going to the bulb, or how much resistance there is. There's definitely nothing about light reaching the bulb. Because think about it, I mean, light doesn't need any time at all to traverse 1 meter. In effect, you might see a 1 millisecond delay because of how long it takes the current to get from the beginning of the wire to the end of the wire. But light does not take that long. Light will take 1 nanosecond. So current takes 1 millisecond to get from the beginning of the
Okay.
wire to the end of the wire because of resistance.
Raf, before we go, can you give us a good summary of what we have discussed today? Put them together. The Newtonian mechanics, the space is absolute, and the relativity is space and time is absolute.
Yeah, so in Newtonian mechanics, distance is absolute. Everyone says that the distance between 2 points is the same. And time is absolute. Everyone says that the time between 2 events is the same. But in relativity, distance is not the same for all reference frames. If you start to move, then things get shorter. This is called Lorentz contraction. And time is not the same. If you start to move, clocks start to tick slower. This is called time dilation. So distance and time are no longer the same for all observers in relativity. But if you put them together, space and time together create something called the space-time interval. That's the same for all observers. And what we saw today is that if you have any event E in space and time, you can define a light cone. This is a cone defined by these 45-degree lines that only light can travel at. And the future of this cone shows all the possible events that can be caused by event T. And in the past of this event are all the events that could cause this event E. So this is the causal structure of space and time. Everything in the future is an effect of this event, and everything in the past is a cause of this event. Okay, so everything in the past is a cause of this event, everything in the future can be an effect of this event. And everything outside of the light cone cannot impact the event because those travel faster than the speed of light, and we know information cannot travel faster than the speed of light. So nothing outside the light cone can be a cause or effect for this event. Yeah.
Isaac, you want to give a summary?
Yeah, so Ref already gave a pretty good summary. One thing I'd like to add is that in Newtonian mechanics, or Galilean relativity, distance and time are the two unchanging things. Meanwhile, or let's write R and T are the two invariant things. Meanwhile, in relativity, this godforsaken thing, also known as the space-time invariant, is the only invariant thing, which, as you can see, is a combination of both the radial vector and the time component, or, well, CT, which is just a proportionality constant at the end of the day. So, in Newtonian mechanics, R and T are constant.
Is this Pythagorean theorem?
Yeah, well, kinda. Raf can explain more in depth, but it's kind of.
Raf, how can you explain this one as Pythagorean theorem?
Yeah, this is the Pythagorean theorem in 4 dimensions. So
Okay.
yeah, I can briefly explain it. So let's say
Yeah, the first thing I was ever confused about is, oh, that's obviously the Pythagorean theorem, but why is there a minus sign? So can you explain that?
that'll probably take some time to explain, but let me give you the brief idea. So this is a x and y. Okay, so this is Newtonian, right? This is just x and y.
This is Newtonian.
And this is x and ct. This is a space-time diagram.
This is relativity.
Yeah. I'm going to draw a triangle on both. and I'm going
Okay.
to apply a
For
Pythagorean
X
theorem.
and Y, the first one, use the 2 cat example. So 1, 1, 5, 4.
Okay, let me just draw a triangle. And let's call this small distance in the x, let's call it dx. Small distance in the y, you call it dy.
So 4 and 3
Yeah.
and 5.
In the example of the cat, this would be 4 and 3 and 5. Yeah. But in general, you can write just a squared plus b squared is c
Equal to
squared.
C squared. Okay, great.
Here, you can do the same thing. This small step is dx. This small step is dt. And this is ds. So when you apply the Pythagorean theorem, this is going to be dx squared, but minus, oh, there should be a c here. But now there's a minus sign because time is a different dimension than space. And I can explain where this minus sign comes from, but I think I have to explain next time. There's a deep reason why there's a minus sign here. It
Yeah,
reflects
something,
the fact.
Minkowski, spacetime metric, blah, blah, blah. No, I'm just kidding.
I'll see you tomorrow, everybody.